Alright, this is Mr. Gillum, and today we're going to talk about rectangles, which are a special type of parallelogram. Just a few special things about rectangles that we're going to take a look at here, but all the other properties of the parallelogram still apply to the rectangle. Let's take a look here. A rectangle is a special type of parallelogram in which has four right angles, and its opposite sides are still congruent. All these things that we know about parallelograms are still true, except for the one special quality of a rectangle. Sorry, two special qualities of a rectangle are that all the angles are right angles. So this is a special property, and also the diagonals actually not only bisect each other, but are congruent. Okay, these other properties of rectangles are just constant with all parallelograms. Okay, opposite sides are parallel and congruent. Opposite sides or angles are congruent. Consecutive angles are supplementary, and diagonals bisect each other. Those are all common with all parallelograms, but specifically for rectangles, a special type of parallelogram because it has all right angles and the diagonals are congruent. So let's take a look here at the next part. This is just emphasizing the importance of how the diagonals of a rectangle are congruent. Okay, so this entire length km is equal to this entire length jl, but also since they are all bisecting, all of these lengths right here, if we said this is O in the middle, JO is congruent to MO, is congruent to KO, is congruent to LO. They're all congruent little segments in there. Okay, so let's use this information to solve this problem. It says a rectangular park has two walking paths as shown. If PS is 180 meters and PR is 200 meters all the way across, oops. Okay, find QT. All right, let's see here. Well, QT would be from here to here, this length. So what I know about this diagonal from P to R is that it's 200 meters. That tells me that this guy right here is 100. This guy right here is 100. Well, if I know for sure that each side is 100, then I can also say that this must be 100 and this must be 100 as well. So if I'm asked what QT is from here to here in the middle, I would know that it is 100 meters. Once again, I know the diagonals are congruent, and I know that each diagonal bisects the other. So if this bisects and there's 100 left on each side, then that follows that QS would also be bisected, and there would be 100 on each side of that. Okay, let's take a look at scenario 2. It says if TS equals 120 meters, find PR. So if TS from this middle point here is 120 meters, find PR, which is this entire diagonal. Well, I know that if this is 120, this is 120 as well because it's bisected. And so the total length would be 240 meters, or 120 and 120 here would be additionally 240 meters. So PR, which is the entire diagonal, will be 240 meters. If angle PRS is 64, find measure of angle SQR. So if angle PRS is 64, and we need to find SQR, I would know that SQR is, there's a relationship here. This guy is 64, and I know this is a total of 90 degrees. I know that this guy right here must be, let's see here, 26 degrees. All right. So what I have here is 64 and 26. I must also have another 64 and 26 because I know that these are an isosceles right triangle, or sorry, an isosceles triangle, not a right triangle, and 26. This must be 26 and 64, and this must be 64 and 26. All right, I know they're isosceles triangles because I know the distance from here to the corner and from T to Q, those are the same length, and therefore the base angles are congruent. If I know that this is 64, I know this is a right angle, this must be 26, and this is 26. If I'm looking for angle SQR, I know it must also be 26 degrees. All kinds of geometry in these. if we said we had a quadrilateral here and it's a rectangle, that guarantees me that these are right angles. I don't know that that's really going to help us right now in this problem, but it says measure angle KJL is 2x plus 4. So let's see here, KJL. So this angle measure is 2x plus 4. And angle JLK is 7x plus 5. We would have to find the variable. Okay, well, the nice thing about this is that I know that these parallel lines have alternate interior angles here. This angle MLP, must also be equal to angle KJP because they are alternate interior angles. So I know this angle is also 2x plus 4. Now it's important to read the directions so I know for sure. Since it's a rectangle, it has 4 right angles. I can guarantee that this side right here is worth 90 degrees. That little, that MLK angle is 90, and it's made up of 2x plus 4 and 7x plus 5. And they're not a linear pair, but they are, I don't know why they would be a linear pair. They are complementary. So 2x plus 4 plus 7x plus 5 equals 90. So 9x plus 9 equals 90. And now it's just a matter of the algebra. X must equal 9. Okay, and let's make sure we are answering the question. It just says to find x. It doesn't say find the measure of angle anything. So I can stop there. Okay, so just keep in mind we are still parallelogram. These are still alternate interior angles. All right. We get another little theorem here that says if the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. Okay, so it's like the converse of the one we just talked about. So if this diagonal is congruent to this diagonal, then I know that WXYZ would be a rectangle. Okay, meaning that it has 4 right angles and is a parallelogram. All right, so let's take a look here. It says a community recreation center has created an outdoor dodgeball playing field. To be sure that it meets the ideal playing field requirements, they measure the sides of the field and its angles. If AB equals 60 feet and BC equals 30 feet. Okay, let's make sure it says, doesn't say anything about it being a rectangle yet. It says CD equals 60 feet, AD equals 30 feet, AC equals 70 feet, sorry, 67 feet, and BD equals 67 feet. Ding, 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 that's that theorem we were just talking about. Okay, explain how the recreation center can be sure that the playing field is rectangular. I would say something like the diagonals of the field are congruent. Therefore, that's a little abbreviation for therefore. It's 3 dots, like a triangle of dots, therefore. Or you can write out the word therefore. Therefore, the field is rectangular. Or we can abbreviate the theorem that we just looked at. So I would abbreviate it maybe instead. I would say if diagonals are congruent, or you could abbreviate like that, comma, the parallelogram, whatever we said, what is it called? We decided it's called ABCD. Parallelogram ABCD is a rectangle. Okay, we could also put that on there. That's the theorem we're really talking about. It's just the converse of the diagonal theorem about a rectangle. Okay, it just goes back and forth both ways. All right. Finally, we have this nice little diagram here. It says that quadrilateral PQRS has vertices, and they're already plotted. So for us on here nicely, it says determine whether PQRS is a rectangle by using the distance formula. Okay, well, the best way to tell if it's a rectangle or not is to see if the distance between its diagonals is the same. Okay, the distance of its diagonals is the same. So from P to R, if that is the same distance as it is from S to Q, then I'll know that it is a rectangle. So it says to use the distance formula. I prefer the Pythagorean theorem. If I connected these points right here, all right, and I wanted to find that length, I could just make a right triangle here if I draw some auxiliary lines. All right, so you can always use the distance formula for P and R. okay, and find the distance between them, it should match the distance between Q and S. However, I like the Pythagorean theorem because I think it's easier. I can just count the distance 1, 2, 3, 4. This is a distance of 4, and 1, 2, 3, 4, 5, 6, 7. Distance of 7. I know 4 squared plus 7 squared must equal the hypotenuse squared. We'll call it c squared to keep it uniform. 16 plus 49 equals c squared. 65 equals c squared. So I know the c equals, let's see, that's 13 times 5. So unfortunately, there's no way to reduce that. C equals the square root of 65. So my first diagonal here is worth the square root of 65. That's the distance between P and R. Now I need to find the distance between S and Q. So once again, I could use the distance formula. In fact, I better do that just because so you have an example of each. If I'm looking, I'm going to do that one in pink. Between S and Q, I can just find the distance using these coordinates. Remember, this is x1 and y1, the first x and first y, x2, y2, and I can use my distance formula. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared, and the square root of all of that, which is essentially the Pythagorean theorem if I drew in some auxiliary lines. But just for the sake of doing the distance formula, let's go ahead and plug those numbers in. I have negative 7 minus 1 squared plus 0 minus negative 1 squared. So D equals the square root of 64 plus 1. D equals the square root of 65. I kind of combined some steps here. I knew that negative 7 minus 1 was negative 8, and negative 8 squared as a quantity would be a positive 64. I also knew that 0 minus negative 1 was 1, and 1 squared is 1. So 64 plus 1 is 65. As you can see, the diagonals are congruent. Therefore, it must be a rectangle. Okay, so now I have determined that, yes, it is a rectangle. I think that's it for today.